don't think that we do
Let's start the second batch of sessions, which is a bit longer than this one. We have several sessions now up to almost 7 o'clock. So I hope you will enjoy it. Stay we have several presentations now in the beginning that are related to verification and scrutiny and testing. And I'm pleased to introduce José Luis from Egator, who will give an overview presentation of SMART 2014, which you can combine as a guide with sense, boost, and test to do more verification of your software.
Thank you. So, good afternoon. As it's been said, I'm working for Egator. Egator we developed that mostly known for developing the NAT compiler, the NAT compiler, and over the years we have been working on different technologies around data that could be helpful for developing, verifying, or helping people developing software easier in a more reliable way. So one of the things that I'm going to present today is about formal proof and testing. And the idea is that along the years, there is the interest around formal methods, formal proofs. It's been increasing quite fast because of a few things. First thing is that now computers computers are much more powerful these days. So when you want, formal proofs are inherently quite complex. So it means if you want to do them with a computer, you need quite a lot of processing power. We didn't have that 30 years ago, but now we have it. With all the new computers that you buy, they are very, very powerful. So that we can afford to tell the computer, please perform all this static analysis for me and tell me what you think about this code. That's one of the things. But still, I mean, it's not only, there is another limit to formal proofs, is that it's not only the computer that limits you, it's the user, it's the person that is writing the code, the person that is writing, let's say, the contract, the properties that you want to test, to verify in your system. It's not easy. Not easy for a human being expressing in a, let's say, mathematical way the behavior of a system. Sometimes you may do that, but some of the times it's quite complex, or even it may even not be feasible. So the option is to rely on what we have been relying for a long time, which is testing. The most common way of making sure that something works. How do you make sure that something works? You test it. You test it as much as you feel is needed, and then if the testing campaign is fine, you have a certain degree of assurance that the software is doing what it has to. So that's the things that I'm going to talk today, and try to provide you the means to do all these things. And well, I will start with a very quick overview, of safety critical part of the evolution of the language, of the AI-related languages. That will be very fast. Then I will enter into the matter of the talk, which is about the Spark 2014. What is it? What is that language, and why would you like to use it? Then I'll tell you a bit about what I've been talking, how to do modular verification by either formal proofs or testing, and how you combine them. Then I will tell you a few conclusions about that, about the status of the language, about the status of the tools around it, about feedback from people using it. So first, rather quickly, something about language. So first, why is Spark derived from Ada? The main reason is that Ada, from the beginning, has been designed to be clear, to be precise, and to have very well-defined semantics. And this is one example, for example, how when you compare something written in Ada and something written in C, if you look at them, well, I have to say I feel easier to read this Ada code, but then that's normal. I've been working with Ada for a long time. But then it's not only about how easy it is, because if you have some practice, if you read C and Ada quite easily. The thing is that there are many things that make things much more evident. If you want to say that you have a variable and you expect that variable to get a value from the execution of a subprogram, it's quite easy to say, okay, this is an out variable, and be done with it. You know that it's the value of that value when you call the procedure and you put something in test. The value before the execution of the subprogram is, if you don't care. If you put a star in C, doesn't mean that that's an out value. It means that it's something that you can modify, but you can also read it. So it's not as precise as you would like. Same thing for input variables. But as I said, there is some more things in the Ada language about semantics of the language. One of the things, for example, we distinguish a test. When you want to test whether something is equal to something, we don't write it the same way as when you do an assignment, because they are things which are completely different in nature. When you are comparing, you are not modifying anything. When you are assigning, you are modifying something. You want to be clear about that. You don't want to mix, like in the while loop in C, you don't want to mix things of very different nature. You're mixing the assignment test and the end of a loop, all in a single line. Well, people like in C, they may say, okay, yeah, because we don't need to write anymore. This is clear, this is concise, that's fine. But I find much easier to understand the behavior of a system when you have clear boundaries between what the different things that the program is doing. But again, that I could say it's a matter of taste. There are other things which I would think are more important. It's about the behavior of your system. And this is, well, this Jean-Pierre told this thing at the beginning of the day today. I mean, buffer overflows, all these things. I mean, still, we're in 2014, and that's still an issue with C. Why? It's so easy to get rid of that. I mean, you simply need to know what with the things you are dealing with. When you know that you are dealing with an array of such things, then you know what you can do with it. Don't try to write the memory which is just after your array, because that's not what you want to do. And that's what C will allow you to do. And, well, one interesting thing is to be able to detect that at the execution time. Because at least there is no damage. You execute it and you are not modifying what you are not supposed to be modifying. But what is much better for a developer is to be able to be sure that that thing won't happen. And these are the kind of verification that we may get with languages and tools like Spark. With Spark, you run the tool, and it will tell you either no, you will never have any buffer overrun here, or it can tell you, okay, you may have a buffer overrun here if this condition is true and this condition is true. And that's what we want with these, let's say, new kind of tools. To be able to know in advance, statically, before executing things, how your program will behave. So just very quickly, we can say, as an outline of what we have said, the thing is that if you use languages like Ada or Spark, with respect to C or similar languages, you can very easily get rid of buffer or integral overflows, any kind of overflow, because inherently in your language you have all the information about the types, the objects you are dealing with, so that you can detect either at execution time with Ada, with normal Ada, or with languages and tools like Spark. You can detect them statically and know these problems before you execute. Well, just to give an idea about how to put in context this Spark 2014 language. Going very quickly, we saw this morning that, well, there are a few interesting things that appeared in Ada 83, which are still in the more recent versions of Ada. Basically, if we have to choose one of the things that are more interesting are modularity. You can develop modules independently, and you can link them together and make them work together. Support for generic things. You do write an algorithm that can work on several different times, but you write it once. Of course, one of the basics is safety. Typing system in Ada is one of the biggest things we have. And support for tasking in the language. We have seen this morning a very nice demo about how to use tasks, how easy it is to write tasks. This morning there was a question about how would it be much more difficult to write the same thing in C. And I can tell you, it is. It's much more complex because I'm working on the runtime system for the compiler, and we know the things we have. Basically, the idea is we have base tasking in Ada, and we translate that into the equivalent calls to the threading system underneath. And we have to do many, many things to make things right. So it's very complex doing the things correctly in C. Much more easy to do in Ada. Then ADA 95 came with object-oriented programming and some addition to the tasking system, which is the use of protected objects that we have seen this morning as well. Then, after that, ADA 2005 was quite influenced by nice things that we have in Java. And one of the nice things that we have is interfaces, and then we introduced that into the language. And something interesting as well that was introduced is the notion of containers. Containers are very, let's say, are big libraries of types or elements that you use very usually in your code. Many times you have the need of defining a set of things, a list. So that is already predefined in ADA. You have the support to use them very easily. And then, in ADA 2012, the big thing that was introduced was contracts. And with contracts, the possibility of entering in a much more easy way into the formal proofs world. So, parallel to that, so this is the evolution of the ADA language, there is the evolution of the Spark language. And the Spark language originally, and associated to ADA 2005, 95, and 83, was a language where, as there were not contracts in the ADA language, you put contracts in comments, and then the tools could know that they were contracts. And you have to restrict the ADA language that you use so that this tool can be applied and you can get the formal proof analysis of your application. Then, as I said, there were in ADA 2012 there were the contracts, and then it was the possibility of saying, okay, we have contracts in ADA now. We have a similar concept of contract in the Spark. Why don't we merge them together? And that's one of the things that happened with the Spark 2014. First thing is try to get use of the new ADA 2012 language and use what you can already use in ADA for writing in a Spark code. Second nice thing about doing that is this contract magically become executable because they are part of the ADA language. A contract is a place where you say, I am expecting something from my caller, I am doing something for him. But these things are inherently, they are checks that are performed at runtime. So it means that if you want the contracts, you can use them both for analyzing statically your code or for verifying at execution time that the contract is well respected. And at the same time, we say, okay, coming from user experience, we know that there are few restrictions in the Spark language that some customers would like to be removed. So let's try to see what we can do in that respect. So we came to be able to write code like this one. And as I said, in the contract, in the programming by contract paradigm, the thing is that you say, okay, I am a super RAM, in this case, this one, first, I am expecting that people calling me are doing something, which is represented by the pre keyword, which is the precondition. It means that people calling me, they need to respect these things. These things can be checked either at execution time or by analyzing your code. And then you say, okay, if you're respecting, and then we are going to see a bit more into details what these different elements mean. But for now, the only thing is that I want you to know is that the precondition is something that the caller needs to guarantee. And then, if your caller guarantees that, you say, okay, if you give me that, in exchange, I'll guarantee all these things, which is the post-condition, which means post-condition is a mathematical representation of the behavior you expect from your program. Means it's basically design information. It is, for example, if we take a much simpler function, imagine a function which is I will increase the value I receive as input. The post condition can be simply, okay, the value that I will return is 1 plus the value that I have at the input. Plus, you may want to say, okay, if by adding 1, I'm going to be outside of the boundaries of my type, the result will be this one. So the post condition is the design, the information that says, okay, this is what my program is supposed to do. And then there are some other things, which is global is outside in 2012. It's about accessing global variables and depends. We'll see that later as well. It's a Spark 2014 thing, which is there to let you represent information flow of your program. Basically, in the depends is when you say, okay, my output value will be computed using the input value plus a global variable that is somewhere. So that's basically how a contract looks like. This one is a Spark 2014 contract. It's not an ADA contract, but an ADA 2012 contract would be the same, removing the global and the depends.
Would an ADA compiler be allowed to be able to compile this, just ignore the specific stuff?
That's the advantage of using aspects. So this is what the with something is introducing aspect, and aspect is some additional information that you pass that it's not that the compiler doesn't need to interpret that information if it doesn't know how to do it. So it's basically where you may define an aspect if you are developing a tool for, doing any kind of static analysis. The idea is that you define that separate aspect, and then that aspect should be ignored by the compiler or other tools. As we said, ADA has always been one interesting part in ADA was its typing functionality. And there is something interesting is that with ADA 2012 now you can do with types. You can do much things. You can export the notion of contract also for types. And you can define things like what is at the top, which is type predicates, which is basically how to define properties of these objects. In ADA, before that, you could define a type like my type is, for example, a new date with range, you could define. I could want to change the boundaries of the type, but you couldn't take a type and say, okay, I want a new type which is basically this element and this element and this element. At least there was not an easy way to do that. And now you can do that. You can, for example, select elements from types with type predicates. You can define some more evolved characteristics of the type, which are, for example, you can, like in this case, it represents a message, and the message comes with a date when it was sent and the date when it was received. You can represent things like, I want to make sure that the date when the message was sent is always before the date when the message was received. This is the kind of expressiveness that you can get. Or you can, well, this is, I think we're not going to go into the details, but you can also define this kind of characteristics for private types that you are using through a specified interface. That's mostly a detail. So let's go into talking about what is Spark 2012 and what gives you. So there is first the history of the Spark. Spark was, I don't know when there was the first version of the Spark, but it has at least 20 years. So the first Spark language was defined first as a subset of Ada. They took Ada and they said, okay, this is the subset of Ada that we consider safe. So this is the part of Ada that we can use. And on top of that, we are going to add all the contract information that we need to perform formal proofs on Ada program. And they did it, and they had to do that using comments, and a special kind of comment, because the compilers with the Ada language didn't have that, so the compiler needed to be able to skip that part. And with that, you could do mainly three things. First, and this is probably the thing that is more widely used by users, is that I want to make sure that there will not be runtime errors. That when I am accessing elements in an array, there is no possible way of trying to go outside the boundaries of the array. I don't even want a runtime exception being raised. I just want the tool plus the design of my application telling me, don't worry about that. There will no be a buffer override. Then with that language, could also verify that the flow information that you added was correct. When you were saying, okay, my procedure is only reading this and this and this variable, the analysis tells you, yeah, you're right, that's correct. We're only using these variables, no other variable. And the third thing, a quite important thing, is functionality correctness. When you say my procedure is doing this, and I describe this by a contract by saying, okay, I am going to increase the output value by 1, the analysis tells you, yes, you're right, you are respecting your contract. And then, as I said, Ada 2012 came in with the contract language within it, and then the idea was to try to get use of that by using the contracts as something that is that can be formally proved, but also you can run them and verify at execution time that this contract has respected. Let's try to make the language bigger so that users are not that much restricted. And well, that is about trying to be able to have a mix of testing and formal proofs for verifying your system. And well, that is a typical line that we have all seen about how expensive is to fix a problem within your development process. The problems that you detect late are very expensive to fix. So the goal, as any other tool in the world, is try to detect things as early as possible. And how? One of the things that we try is to be able to mix formal proofs and traditional unit testing. So if you have a look at the typical development cycle, the thing that Spark tries to address is everything that is within these boundaries. You can define and verify architectural information, low-level requirements information. You can do things with the code. You can make sure of the robustness of the code. You can use that for verifying different units that we develop. And you can, well, of course, verify the architecture that you define. And the thing is that we try to follow the information we get from customers, saying, okay, the most expensive part of our development is testing. And in addition to that, it's not perfect. So you tell me, okay, I can try to prove things, that I can remove tests. But the difficulty is that sometimes if I want to do that for all the system, it's very difficult. And there is a part, there is typically a part that you can formally prove in a reasonable way, but there is a part which is very complex. So the thing and the goal is to be able to do formal proofs on things that are practical to do that, and do typical unit tests for the rest. So here is the kind of things that we want to we use within the new Spark 2014 language that come from the ADA language, the ADA 2012 language, which is the contracts of both subprograms and types. And there is a new kind of expression that is very handy for writing these contracts, which is this kind of quantifiers, because you can do, for example, we can ensure properties in all elements of an array or a set, or in some, so it's very flexible. So as I mentioned, well, we are not going to see everything because it's not very interesting, but one of the things that you can express in the new language is the way you access through global variables. When you implement your program, you need to say, okay, I want to use this variable as an input, this global variable as an input, or as an output, or both input and output, and that you can define with this syntax, where you basically put on the right side the inputs And on the left side, no, this is not. This is the defense. This is only where you say things that are used as input, output, both input and output, or eventually you may want things that are only used not by the implementation, but by the way you define your content. So that's simply that. You can also define how the information flows within your subprogram, and you can use this kind of aspect, which is the defense aspect, where you basically say, for example, if you take the first line where you say AB arrow plus A X and Y, well, the plus is simply to say that I am depending on myself. I am computing my next value based on my current value. This is the plus. But if you skip the plus, it means that A and B, they use for the next value, they are using A, X, and Y. So that's the kind of information that you can express with that. And well, this is a small example where you basically are saying that when I'm computing my new G value, which is, by the way, a global variable, I am taking into account the two input variables that I'm having here. So this is how you express the flow information. In terms of the subset of data that is supported, well, there are a few things that are not yet supported. Some because it makes this global analysis very complex, and that's, for example, that's the reason why pointers access type are not supported. And there are some other things that are expected to be in the language but are not there yet, such as tasking. Tasking will be there but not yet, and tag times will be there. And this is an outline of things that has been added. For example, support for generics has been added, and a few more details. Nothing really very important. Another thing that is being added is support for formal containers. As we said, containers is a library where you have access to common data types such as lists, sets, etc. Typically, the way you implement them is by using pointers all around. That's the way you keep a list ordered, by changing pointers. So they are inherently not used. You can't use them with this Spark 2012-14 language, but we are working on defining new containers that can be used in this context with all the properties that are required that will be formally defined for you to just use them. Some additions, for example, an evolution of the way contracts can be written in ADA 2012, but that we found quite convenient, and that's why we put that into Spark. It's what we call the contract cases. We noticed that many times when you write a contract, when you write the behavior of a subprogram, it's very common that you write, okay, if my input value is positive, then the result is this one. If my input value is 0, my result is that. If my input value is negative, my result is that. You can write that with an if statement like the one on top. But we find that it's easier to read if you define what we call contract cases, where you put the condition before. It's similar to a case statement. So you put the condition and you put the result afterwards. So it's a matter of convenience. I mean, you don't gain anything. There is nothing. I don't think there is anything that you can write this way that cannot be written that way. But it's much easier to understand. With respect to the behavior, there are some things when you try to formally prove things. It's quite common that you need to say determine. I mean, loops are not easy, and sometimes you need help to demonstrate the things that change and doesn't change within the loop. And this is what we express with the loop invariant, which says, okay, this is not going to change any iteration of the loop, and the loop variant is going to say, okay, this is the thing that is going to increase, so you know, or decrease. So you know that if you have a condition which is while I is smaller than 10, if you know that I is increasing, and you start with a value which is inferior to the boundary, you know that eventually you will get there, and you'll leave the loop. We are going to pass quickly this part. So basically, the idea is what this is a certification, DO 178 avionics certification, which basically defines the different parts of the development. And the thing is that what we try with the Spark is to be able to help you into making sure that the code that you write is the code that is expected from the definition of the architecture that you did. We want to make sure that the code is robust. It means we want to make sure that there will not be an exception being raised anywhere, say, because you wanted to access something that is outside the boundary. And we want to make sure as well that the code that is written is compliant to the contracts, to the definition that you did before about what the code is supposed to do. So, well, basically, what we try is to do that, mixing these two different approaches. So what can you do in terms of dynamic tests of verifications that you can do at execution time? So basically, preconditions for postconditions are simply assertions. So it's something that you could even write before having contracts, but it's much more convenient to write them as contracts, because with contracts you put them into the specification, into the visible part of your program. And if you put assertions within your implementation will be quite polluted by the presence of assertions everywhere. Imagine that you have a code where you have 3 different return statements, and before all that you need to check the return that you are going to, the value that you are going to return. It's much easier to write it once and let tools take care of that. And you can control those contracts that you want to be active or not at any time. As I said, contract cases is the same thing, it's contract, but you can write them in a more convenient way. And the advantages of being able to execute the contracts is that it gives you very quick feedback during your development about whether you are really implementing what you are expected to implement. Obviously, during testing is very valuable because you could even define your tests without specifying the expected results. If you are able to define completely your behavior with a post condition. Imagine the same example is if you define a function increasing the input value, and you define test cases for that, and you know that the post condition is, okay, my output will be 1 plus my input, that's enough. You don't need to say, okay, if I put a 3 as input, I expect a 4 as an output. No, that's implicit within the contract. So that simplifies testing. And you can use them as defensive programming at execution time when the system is deployed. And in terms of formal validation, basically that these are the 4 different things that you can do. Data and information flow, which is about I am really using the variables that I'm expecting to use, and I'm really computing my output, taking into account the input that I wanted to use. The robustness analysis is whether I'm going to have any exception raised at execution time. I might try, is it possible that I can try to access an array outside of its boundaries or not? And of course, checking that you are implementing what you said in the contract that you were going to implement. Well, that's basically, once you have put all the flow information, you can make sure that you are using input variables as input variable, output as output. You are not trying to use something that is not initialized yet. And you can do this kind of analysis very quickly. Same thing with respect to global variables. You can make sure that you are using them as you define you were using them. For example, here, if you are modifying, if your code is modified by global variable g, and you didn't say that in advance, the tool will tell you, you are doing something that you are not allowed to do. Okay, the same thing for an initialized variable. You will get messages saying, okay, here you may be trying to access something before being initialized, so you will be using an unknown variable. As I said, one of the most interesting things is to be able to make sure that there is no exception being raised within your execution. You can make a static analysis and make sure that all these different checks will be respected at execution time. And you can make sure, for example, that there will not be any division by 0 any place in your code. And of course, you can make sure that that your code respects the contract that you are making visible to the user. And then the contracts are checked. Preconditions are checked when the program is called. Post conditions are checked just before returning. Yes, that's how information is presented to you. If you do the static analysis, you will see in red the lines that may not be respected. In this case, we are saying that the loop invariant that is present here might fail after the first iteration. So it means the first iteration, that will always be respected, but the second may not be true. So that's what the feedback you get. There have been a few case studies, and I will show you quite quickly the kind of feedback that we got from there. Basically, what this is, the different lines refer to different pieces of their code. The important information is here in this column. We have the number of subprograms, and here in this column is the number of runtime checks. If you access an array, there will be an index check. So this is to give you an idea about the size of the different modules. And this is the percentage of things that they could prove formally. And you can see that they can reach quite big values, and they could even get to 100% in some cases, and quite close in some others. So just to conclude quite quickly, the thing is that if you really need to go to the highest levels of safety, this kind of technology has already been. It comes from feedback from customers working in this kind of domain. And it is a technology which is already in more than 20 years being used, at least the core part of it. And the good thing is that with the new Spark 2012 and its very close relationship with Data 2012, you can start using that language slowly and progressively. You can start developing one module using that, but the rest you keep doing them as you were doing before. So it helps you build up all these formal proofs if you need them or if you want them. Well, basically here, it's about areas that where this technology works well, and we detected some places where we needed to improve the technology. And that this is something that is going to be available very, very soon. We have, this is being beta tested now, and the first release is expected in 2014, April 2014, so just 3 months. And well, you can have access to this web page where there is the design information, much more detailed information about the language, about what is supported, what are the technologies we use, etc. So that's the place where you can get some more information if you are interested. And that should be it. That's it. Thank you. If you have any questions.